Hello, good evening, everyone. So, welcome back. You'll be at 2 in our last class. Today we'll discuss about congestion distribution and policy analysis based on IFN. And I hope you can also find out, check presentation. So, maybe in the end of this. Yeah, so I know everyone has been working hard, probably one more time to polish the report that show commitment. So I appreciate it. So, but tonight is our last schedule, our last class under the UP academic calendar. So next week is the final exam. So we cannot move the presentation forward. So I think that presentation is, so you should think this as not the final performance, okay, but as the chance to share your key finding and get the feedback. You still can polish the detail that you will reflect it your written submission next week. Is that okay? Right. So just present a report or slide, okay, even if it is not perfect yet, okay, it's okay. So what matter is showing your analysis, your process, the insight you have developed. So that's what I will look for, okay? So, well, I strongly encourage each group to present tonight. So this is your opportunity to demonstrate your work and ensure it is recognized. So if you hold back, you will lose that chance. Okay. So while preparing for that, so you can start with our lecture. Go to Moodle. There is a slide about congestion redistribution. Share with you. Okay. So this is the concept I developed a few years ago. Okay. So you have the knowledge during this semester about ideal flow network, right? So I would like to introduce the new concept of congestion redistribution. Okay, so this is the application scenario. Can you see in this table? So what are the policy that you can do in transportation, and then we put it into atomic in the graph theory level. Okay, so what you can do to change the situation right now. Okay, so one of them is to change the link. Yeah, the other one is to change the node. Okay? Or you can change the network or sub-network, okay? Or you can change the path, okay? Or you can change the stochastic matrix. Okay? So the one that changed the links, I put it here. Okay, so if you want to change the link, okay, there are two ways. One is to change the weight of the links. The other one is to change the structure. So of course, you can either add or reduce the weight. In the structure, you can add or remove the link, right? Or change direction. Yeah. So when we say you change the weight, that means either you add lane or reduce lane, number of lanes. Okay. Similarly, some people don't care about the actual lane if they prefer the width. So in meter, and so you can add the width or reduce the width. So then we think about it whether it is permanent or temporary. And so these are the uh, use cases, application scenario. So if you want to add the lane, okay, temporarily, that means you remove, for example, on-street parking, right? Or if you want to add the lane permanently, then you provide additional lane. So that additional lane is usually about 3 meter to 3.5 meter, 4 meter. Yeah. So how about if your policy is to reduce the lane? So again, temporary or permanent. Yeah. So if it is temporary, that means these are the scenario, right? So either you do on-street parking allowance or certain events that you do, yeah, uh, along the street. So, for example, there is a bazaar or market, okay, in the weekend, or there are certain event like protest or demonstration or religious event. I noticed you have a lot of religious event and or festival, or there are certain VIP will pass a certain lane. These are reducing the lane, but temporarily, yeah, on certain time. Or you can reduce the lane permanently. Yeah, this is reduction the lane for the car or bus, other vehicles, but you may use it this lane for bike lane, for example, or for public park. So yeah, or for pedestrian. Similarly, you can also uh, uh, do it based on road width, yeah, rather than the lane. Now you can also change structurally. Yeah, so meaning you add link. Yeah, if you add link, that means uh, at certain road, right, or certain bridges. Yes, either temporary bridge or a new road, yeah, or a toll road and so on. That's represent a path, yeah, toll road. So uh, if it is temporarily, so that road is removed from the network, okay, for a certain time. For example, night market will occupy the whole street, or certain events, yeah, will occupy the whole link. Okay, this is these are the policy that you can also uh, check using transport model. Okay, or you can also reverse the direction of it. These are the main policy, based atomic policy that you can combine with other. Okay, so in the traditional idea, uh, the question is always which one first, right? Uh, Chicken or egg. Yeah. So until recently, okay, traditional transport planner would say that demand would control the amount of supply. This seems to be the most optimum approach. We let certain road link to be congested. We started to add more supplies. So, for example, we widen the road to cope with the increasing demand, right? So demand will control the amount of supply. So we let certain uh, point, yeah, that the road cannot be widened anymore. Yeah, maybe due to the demand of the space for living or activities, or probably the land price has increased so much. So then the road expansion is economically invisible, right? Unless it is done by the force of the law. Then to cope with the demand of transportation, then we start to build public transportation. Okay, now we prohibit the single use of car, user realign the land use, and so on. So we call this transportation demand management. When we only think that demand control the supply, we can only add supply or control the demand, isn't it? So since our economy and population are increasing, unless there is a war, so adding the supply and controlling the demands are extremely difficult tasks. Yeah, so it is a traditional idea. So a new approach is necessary. Okay. So I have an approach. Yeah, is more holistic. Yeah, based on IFN, we acknowledge that the demand may also control the supply as the past human wisdom. Okay, so we build the road of certain width, okay, because of the past demand. Okay, but we don't stop there. Okay, in addition to the past demand, past wisdom. Okay, so IFN concept open up a new many possibilities. Yeah, based on acknowledgement that supply may also control the demand. So it's the other way around. Okay, that's why chicken and egg or egg and chicken. So the basic idea is having possibility to correct the supply. Okay, so we alter we create a policy that alter the supply in order to make the demand change. Okay, to cope with the supply. Now, the correction of the supply will create new equilibrium, okay, to balance the congestion of the entire network, okay, not just one link. Okay. Now, the demand can actually be rebalanced via supply chains. That's the basic idea. Yeah. So I put it in this drawing. So we can redistribute the congestion, okay, by reducing the number of lane in specific link in the network or deleting a link, not always increasing the number of lane, okay, in such a way to lower the maximum congestion in the network. Okay, so after applying the policy, so for example, yeah, you want to what is called road diet, yeah, road narrowing, or to make the pedestrian only zone. Yeah. So based on congestion distribution, okay, then the maximum congestion of the network will be lower. Okay. So, but the average travel time in the network will be slightly worse. Okay. So that's the basic idea of congestion redistribution. Okay. So similarly, okay, our argument of congestion redistribution, okay, uh, may not be accepted if we keep using average travel time, okay, or average network speed as your performance. Yeah. Instead, we need to use maximum congestion as the performance criterion. Yeah. Why? Because maximum congestion happen only in one or few links. Yeah. So one often mistakenly thought that it is measure of a link. In fact, maximum congestion is a measure in the network, not in a link. Okay. And why this is important? Because if you know the maximum congestion in certain links, then you can measure it there. You can validate the performance indicator. But once you tell about average speed in the entire network or average travel time in the entire network, there is no way, yeah, unless maybe in the future if we can put all the sensor in the network, okay, at this point of time, there is no way you will know the average travel time in the network. So that is telling lies to the public through science. That is not okay. Okay? Because you cannot validate that. Okay? But by telling that this is maximum congestion, that is only a few links. That means you can validate. That is what science work. You don't just do the model, but you can also validate your model, whether it is correct or not, isn't it? Okay. Okay. So before we go to this, is there any question or comment probably? No comment? Okay.
Sir, I have
Yes,
a
go,
comment.
go. Yes.
So does it mean that for example for a for example BGC
Hmm.
BGC uh traffic or congestion is increasing because they keep increasing the both demand and supply. So more office spaces, more residential. And then the role for planners would be to limit that through zoning or yeah. Would that be
That's the traditional idea I
traditional
told
idea?
earlier, right? So the traditional idea is we we keep the demand allowed to increase. Okay. So when the demand already increase, what you will do with that? Oh, because population increase, right? So economic increase, so people want to buy more private vehicles. Okay, that's the normal way. So then you limit, okay, the number of people who come to the area, maybe through congestion pricing, okay, at certain point, or you limit the vehicles through travel demand management by introducing public transport uh, to come there. Okay. So what you do is to change the demand, right? But I'm telling, what if instead of, yeah, okay, that is good, yeah, travel demand management and demand management is good. But what if you can also change the way of thinking? Yeah. So what if you change the supply to change the demand? The supply means the road network.
Okay.
Okay. You
Congestion.
no the road width, the number of
Roadway.
lanes. Okay. And the supply means probably the number of public transport that you have. That's supply. Okay. Remember, the demand is from the population side that create the flow. Okay. The supply means the infrastructure.
Okay.
Okay. So question is, if we change the supply, probably it will also affect the demand. That's exactly what we are trying to do. Okay. And not only that, what if you actually change the information about the supply? Example, Google Map, Waze. Okay. So using this information about the supply, they are telling you, oh, don't pass here, you pass there. Right? So you reduce the maximum congestion in certain links. Can you get the idea? Okay, but you redistribute this congestion. You don't change the demand to other links in the network. That's the basic idea of congestion redistribution. I hope this
Okay.
makes sense.
It makes sense, Prof. Actually, here in our study, um, just getting data on the certain routes is it's hard to get the data online. So
Hmm.
the information is also
It's hard, right?
it's also hard. Yeah.
So in that case, we can use the principle of maximum entropy that we discussed last time. Yeah. So okay, when you don't have data, okay, then you can assume based on maximum entropy. But if you have data, then use that data. Okay. So let's come back to this concept of maximum of congestion redistribution. Okay. So this. Hmm? See my slide? Is it not working? I have some congestion. Hmm, Then, okay, let's come back. Okay. So suppose you have two networks. Okay. Uh, let's call this N1 as your current network. Okay. And then you have what is called policy. So let's name this P as your policy. Okay. So uh, the current network, the base scenario, N1, okay, plus the policy that you want to do. Yeah. This policy can be road widening, okay, or road diet, or additional link or reduce the link and so on. Okay. So then N1 plus P equal to N2. So this is the alternative scenario. Yeah. So in your project, you're supposed to make like this, right? This is the base scenario, and this is the alternative scenario. And then you compare, right? Is that correct? So what do you want to compare? Say, in the first network, the base scenario, you have congestion G1. And this is the matrix. Okay. And in the alternative scenario, you have congestion matrix G2. Okay. So now the definition of congestion redistribution is very simple. Okay. The maximum G2, so this is mean maximum mean only one link. Okay. The maximum of G2 must be less than the maximum of G1. Is it or not? Okay. So based on your matrix, okay, based on your matrix, you will find the maximum congestion. Yeah. This is the matrix congestion matrix G1 from the initial base scenario. And then you have also another matrix G2, right? Now you find the maximum in G2, which is the alternative scenario, must be less than the maximum in G1. What does it mean? Meaning your policy works, isn't it? Okay. Because if your policy doesn't work, your alternative scenario is actually equal or worse. In that case, what is this policy for? Is it? So, so you will find a policy P, our goal, yeah, in order to make so that the maximum congestion, okay, or the alternative will be less than the current condition. Is that clear? So when we stated this mathematically, okay, then we can start to derive. Okay, because if you define, then you can derive. Okay, so earlier I mentioned, okay, when the capacity matrix is premagic, yeah, last time. Okay, So then the congestion matrix will automatically become uniform distribution. Okay. So this condition is called Premachic equilibrium. Okay, meaning balance. So this can be the ideal of ideal flow network. Okay. So many measure actually can be used to measure how close our capacity matrix or congestion matrix to the Premachic equilibrium. This is the ideal of ideal. Okay, so example, I can use relative entropy or entropy ratio. Okay, so one of them, okay, that I developed is called far pi index. Yeah, so this measures the difference between the maximum and the average congestion. Okay, but this is not the usual average. This is the weighted average, yeah, capacity weighted average congestion. Okay, now the closer this far pi index to 1, that means closer to Premachic equilibrium. Okay, next we can also use relative entropy. Yeah? Sometimes this is called uh, Karhunen-Loewe divergent, yeah, KL divergent. Okay, so you can search in Google. Yeah, this is also used for checking, yeah, whether for the congestion or the capacity matrix. Of course, the closer relative entropy to zero, that means closer to Premachic equilibrium. Okay, so we know that relative entropy is actually asymmetric distance. So it is invariant from scaling. So another measure that we can use is entropy ratio. Yeah, closer to 1 means closer to Premachic equilibrium and so on. So, but they are non-linear, okay? So later I will show you the comparison between this, okay? When I generate random network, okay? So here is the one that I use and I put in the program, in the code, okay? What is called far pi index? What's the definition? So you get the congestion matrix G. Okay, so far pi index of G is 1 minus, okay, maximum of that G, that is one number, okay, and then you get the average. This is, be careful, yeah, this is not just the arithmetic average, this is capacity weighted average, yeah. So maximum minus the average divided by the maximum, so then 1 minus of this. So far pi index is a normalized index, yeah. This represents the efficiency. Okay, so between 0 to 1. So what is relative entropy? Yeah, KL divergent, Kullback-Leibler divergent. This is distance, yeah, between two distribution. So you have two values, okay, before and after. Okay, so of course, in this case, because you want to measure toward the Premachic, so you need to put it against the Premachic. Yeah. So the actual compared to the Premachic. How is it? Yeah. So what I'm doing is to generate random network, okay, and compare, yeah, between a relative entropy of the congestion and far pi index. Yeah. So if you look at this, they are almost linear. Yeah? The two of them. Okay. But if you use far pi and entropy ratio, they are non-linear. Yeah? So what does it mean? If meaning if you use far pi index, yeah, they are just scaling of the relative entropy. Yeah, because it's linear, so that means only scaling. Okay, so you can use either one of them. But I prefer far pi. Why? Because this is simple. Yeah? Just maximum and average congestion. And during NFI last time, we already discussed that far by index also. Yeah. So why we want to use maximum congestion in the network? Yeah. Is it better performance than the average travel time and speed? Yeah. Because our goal usually we want to reduce the congestion level of the worst link in the network. Yeah. When we focus in the performance of the network, for example, average travel time, average speed, yeah, the only way to solve traffic congestion will be to widen the road to add new links. That is difficult to, if you reduce the uh, number of lanes, okay, it will usually uh, make the travel time worse. So now, once we free ourselves from the old paradigm, okay, and enter into the new paradigm using maximum congestion, yeah, in the network as our index, okay, then what will happen in the specific links will have a better option. Okay. Now we can both simulate, okay, scenario of road widening and road narrowing. Okay. And we can also simulate the scenario of adding link or link removal. Okay. So the most important part here is if you want to change, okay, in principle, you need to change your mindset first. Okay. If you still, your mindset is still in the old paradigm, okay, there is no way to change to be better because you limit yourself. So to evaluate the feasibility of making pedestrian only zone now become feasible or bike lane you are telling. Okay. So reduction of maximum congestion is actually similar to the concept congestion distribution earlier. Yeah. So that it will become closer to uniform distribution. Okay. So these are the pros and cons, yeah, of congestion redistribution. Yeah. So congestion redistribution will actually reduce the maximum congestion, but it might increase, yeah, not always increase, but it might increase the average travel time. Okay. Using congestion redistribution, okay, there is feasibility of more policy alternative. For example, narrowing road, pedestrian only zone, and so on. So you can do this. Okay. But it might also increase the network delay. Okay. So using this congestion redistribution concept, okay, you will have more efficient use of the road network. Okay. But what is the problem? Okay. It may decrease the network speed and distribute the traffic to the minor road. Okay. So these are the impact that you may start to see. Okay. Uh, and then you can reduce the high concentration of air pollution. Okay. But because you redistribute, that means the air pollution of the minor road may increase. So, but against within certain threshold, it may easily disperse by the nature itself. Okay. So now we go to the mathematics. Yeah, how it works. Okay. So first, you need to understand the notation. Okay. So CB here is the capacity matrix of the base scenario. Okay. And from this base scenario capacity matrix, the current situation, so you compute the flow matrix. Yeah. So this F represents the flow matrix, which depends on the capacity and certain total flow in the network. Yeah. Kappa zero. Okay. So if you don't know kappa zero, no problem. You just set as 1. Okay. Okay. I will show you in a moment why this will work. Yeah? So, and then from this flow matrix and the capacity matrix in the same unit, this is the keyword, the same unit. Okay. Then you will get unitless, what is called congestion matrix, like so F per C Hadamard product, Hadamard division, you will get the congestion matrix. After that, what you will do, you get the maximum congestion. Yeah, so the maximum congestion of G0 is small letter G here. Is it okay or not? Okay, so then what you want to do? You want to get the maximum congestion of the alternative scenario, right? So after the policy, you get G1. So I put star here. Okay. So the technique is to compute kappa 1. Okay. What is this? The total flow in the network, yeah, of the alternative situation. Okay. Which is just a scaling. Can you see that? So if you can calculate G1, okay, divided by G0, which is already here, and kappa 0 is 1, okay, so you can get kappa 1, okay. So in that case, how can we do that? Okay, so you need to have the capacity matrix of the alternative scenario, okay, after policy, okay. Then you can compute uh, F1. Okay, so based on this base scenario and kappa 1, so you can compute F1 to get the maximum congestion G1. Okay, then, okay, we set this scaling factor kappa 1 as our invariance in all scenario. Okay, remember in modeling, if you want to predict, okay, there's something that is invariant. There is something that does not change. That is something that you assume does not change. What is the meaning of kappa 1, total flow in the network does not change? That means your policy is short term. Okay, that means within 1 year, you need to do it. Yeah, meaning the demand does not change yet. Yeah, does not change so much. Okay, so this is called ceteris paribus in economic. Yeah, so now you have the alternative scenario, which is after the policy. Let's call this CA. Okay, because you already set kappa 1 as invariance, so now you can get the new flow matrix. Yeah, so let's call this F1A, and then from there you divide, okay, F1A divided by CA, yeah, Hadamard division. So you will get congestion matrix G1A. Okay, and then from this matrix you find the maximum congestion, yeah, the small letter here. Okay, so remember, congestion redistribution means, okay, GA here must be less than G1. Is this clear or not? So I will demonstrate with you. Okay, I already created several lab, right? So you can go to Moodle, but I can also go directly here. AFN virtual lab, yeah. Okay, virtual lab. That. Okay. You can scan this QR code if you want, or go to this page. In Moodle, you have the link directly. Okay, let's go to the first example, this one. Yeah. So in this lab, I only deal with these five, okay, alternative policies. Yeah? So these are the only policies that I want to simulate here. Yeah? Either we add the link, we delete the link, yeah? We change the link direction, or we add the lane, or reduce the lane. Yeah? Okay, let's go down to the lab tool. Yeah, so if you want to see how to use here. So here I will press this button. Can you see the yellow dice? And this will generate random matrix. Yeah, small. Okay, there. So every time you press this button, it will generate new network. So the network is there. Okay. So now in this lab, what we will do, there are only two policies. Yeah? Either you add or reduce the number of lanes. So this is the network, so I can move this network. Right. Okay. So this is 9 lanes. If you don't want, I can change to 3 lane. Okay. And you can redraw. Yeah. There is this in the middle, in the diagonal should be 0, right? Yeah. Okay. These are example of network that I generate randomly. You can play with this. Now, what do you want to do now? So we can either add or reduce the lane. So these are the only feasible. Yeah. So when you click this button, it will generate the feasible links. Yeah. So AB or AC, this is AB. Yeah. AC is this one. So you can either add or reduce the lane. Okay. So for example, I want to add 2 more lane in AB. Yeah. This is 3. What happened? So I add here. You click this positive button there. Okay, this is the buffer. So if you look at this and then click the blue, okay, so from 3 now become 5. And the rest is the same. Can you see that? Okay, so then you can set the base scenario. Yeah, maximum congestion. This is exactly what the one that we have. Yeah, this one. K kappa 1. Okay. So what is your kappa 1, the base scenario? And not the 0, but the initial, yeah, kappa 1. So example, you set 0.8, yeah, or you want to set 0.9. It doesn't matter. Okay. So when you set this 0.9, example here, base scenario, okay, and then you add 2 more lanes in AB, and so you click this. This is the alternative scenario, is better, yeah, than the base scenario by 1.9%, yeah, based on the maximum congestion. Okay, it will automatically calculate the VAR-PI index and total capacity, yeah, and the total flow also. Yeah. So in this lab, you are only allowed to simulate one policy, yeah, atomic policy. Of course, in the real project, you are not supposed to to only one atomic policy. You're supposed to combine many atomic policy, isn't it? Okay, so in this lab, I've just demonstrated to you that using one atomic policy, you can actually improve. Yeah, so this is one of them. Okay, okay, so then you can report. Yeah, you can report everything here. Okay, and I have also another tool here. It's called optimization. Okay, so it will search for all the policies, yeah, add or reduce lane. Okay, so if you click this button there, yeah, the result is down there. Yeah. So you will start to see the max. So you click this top header. Yeah. So you can start to see the change. Oh. So then you will start to see that changing the best policy is actually reducing CE, yeah, not AB. Yeah, in the network, this network, CE, this one. Yeah, from 9 lane to 1. Remember, we can, okay, what will happen? If you reduce CE from 9 lane to become 1 lane, the maximum congestion will change from 0.9 to become 0.82. Yeah, from 90% to become 82%. Okay, with the same total flow. Okay, and the total capacity actually reduced, but the efficiency increased. Ah, amazing, isn't it? Okay, so far, okay, the way of thinking is, oh, I need to add lane. I need to widen the road. Okay, not always. Okay, if you start to use induced traffic technique, yeah, with this congestion rebalancing, you can actually also reduce. Okay, you can actually reduce the number of lanes. Okay, okay, reduce the capacity, but improve the efficiency automatically. So, any question, any comment? Go. Do you understand the meaning of congestion redistribution? Or give me uh, your feedback. What do you understand so far? So that I will know. Do you want to play here?
Can I ask a question, sir?
Sure, sure.
What's the what is the um operation? Select
Reasonable.
an operation, irreducible, P-magic, stochastic, or ideal flow.
Which one? Which one?
Under the base capacity and an alternative capacity, there's two scenarios, and underneath the networks, there's the select an operation.
Select. Ah, select operation.
Yes.
These are the tools, okay, to check whether this is irreducible or is it premagic, okay, okay, is it stochastic matrix or not, is it ideal flow or not. These are just the tool to check that matrix above.
Okay.
Okay. So try to see, okay, you create a random network, okay, and then check, okay. The same network, you can also put it into the matrix side of IFN. Later, yeah, I will demonstrate that. Okay, Justin, you want to say something?
Sir, for the scenario modification, can only affect one link at a time?
Yeah, yeah. You can add more actually. For example, AB. Yeah. So for example, here I add AC. Yeah? So you want to where is AC here? This one, right?
Yeah, yeah.
So AC 3 lane. So I want to reduce it. So I put here reduce.
Ah, okay.
Okay. So you can combine.
All right, all right.
All right. Okay.
Okay.
So this is the buffer first, meaning if you don't like, you can just remove this buffer. Okay. So say I want to reduce you see there. AC. Oh yeah, it's correct, right? So AB I add 2, this one, and then AC I minus 1. So from 4 to become 3. Right. So then you click this yellow icon. Okay. And this combination of scenario, and these are the reduction. Yeah. So the one that search here is only one policy, yeah. But in here you can create more combination of policies. Yeah, nice. Yeah. So of course this is only up to I limit up to 7 nodes. Yeah. But if you want the real one, so you go to the IFN matrix here. Yeah. You remember we used this last time, right? So you set the matrix here. Okay. So you can also play in here. So you have the matrix, the distance, and the maximum speed. So you need to set the 3 matrices in order to do all. Then after that, you can just compute this. So you get all the result. Okay. So if you want in matrix form, so if you don't like matrix form, you can also go to the actual IFN transform. Okay. So this is the same computation but different format. Okay. So in here I have the node, I have the link matrix, and then you can see the network. And you can even change the network into something else. For example, this is near UP campus. Yeah. So these are the network, right? This is the QC circle. Yeah, I think we are inside the campus. You are around here. Okay. So yeah, the basic idea is not all links are feasible. Okay. So in add and reduce lane, of course, you cannot have something that not exists. Okay. So in the next scenario comparison, add links. Okay, this is only affected the one that 0. So if you look at this, these are the links. You will have different visible links that you can add. Yeah. So this, of course, this is not supposed to. This is like a loop on itself. So anyway, so these are the links that you can add. Okay. And then in the next lab also, yeah, this one is to remove the link. Okay. So the visible link, say for example, okay. So these are the visible links that you can remove. That means one cannot, yeah. Because if you remove it, it may become disconnected. So okay. So we need to maintain that the network is still strongly connected. Okay. So there are a lot of computation in the back, okay, to maintain the stability of the network. Yeah. And similarly, the next lab, okay, reverse the link direction, right? So not all links you can reverse. Again, okay. So yeah, only these links you can reverse. The others cannot. Yeah. Why? Because if you reverse, yeah, supposed to zero in. Oh, yeah. So only these 3 links you can reverse. The others cannot. Why? Because if you reverse the others, it will not become strongly connected again. Yeah. So why, if it is not strongly connected? That means from your home you can go somewhere, you cannot come back. So that's not the way to do transport network, isn't it? Okay, so you need to maintain that the network still strongly connected. Okay, that's the main idea here. Say, for example, if I read at this, yeah, so now BD, yeah, I reverse, what will happen? So B to D, where's the B to D? Yeah, 3 here, right? Oh, but this is already 3. Let me make it different so that you will see. Okay. There. Can you see this? This is 2, now become 3. Yeah, this is 3, now become 2. Can you see that? It's reverse. Okay. So it's reverse the direction. So if you do it one way, for example, you want to create another fashion. So with this also you can start to optimize. Yeah. So you want to find which scenario. Okay. This one is combination of scenario. Okay. Or if you reverse this link direction combination, you can actually improve the congestion level. Yeah, 52%. Wow. Yeah. The point is using the same concept. Yeah, if you understand the mathematics a while, okay, uh, you can actually start to simulate very fast, okay, and then you can start to see that we can do this, which traditional way cannot do. Okay, so let's try for your practice. Okay. This is the myth that always many planners thinking, yeah, that adding lane will improve congestion. Yeah, why it is a myth? Yeah? Because improving congestion in a link, okay, not necessarily improve. Yeah, it might also worsen the congestion in other link in the network. Okay, so why it happened? Because congestion is actually non-linear. Yeah? So if your congestion level is below certain number, for example, 0.8 or 0.6 here, you will see this is almost linear, right? But once you go above certain numbers, 0.6, suddenly it becomes non-linear. Huh? So the delay and the travel time become more severe. Okay. So now let's prove this, that this is a myth, okay, by reducing the lane to improve the congestion. Yeah. So if we can actually reduce the lane and then we can improve the congestion, that means we disprove, yeah, the myth. Okay. So now I hope you can try so that you can understand the values. Can you try this capacity matrix as your base? Okay. So you type this in the lab. Okay. And you set the initial maximum congestion 0.9. Okay. And try to reduce this DE here, the one that I put set as red. Okay. And then test whether the alternative scenario with this exactly the same network, except now you reduce, yeah, from 4 lanes now become 2 lanes here. Okay. Whether the performance is better or not. Can you do that? Yeah. So the answer should be like this, yeah. Okay. So once you do that, so you show your work and you share your screen. Is that okay? Yeah, simple practice this one. Yeah. So what I'm doing first, I will compute with K0 equal 1. Okay. So initially I don't know, right? So what I'm doing is I've set the K0, it is the total flow in the network, equal 1. What happens if I do that? The flow will become probability. Yeah? This will become link probability. The ideal flow will become probability. So once you have that, okay, now you can set, this is the example. I use Excel. Okay. When you set 1, this will become probability and maximum congestion, certain numbers. Yeah. So this is probably not true. No problem. And then what we will do is we set the target, okay, K1, which is, no, the G1, which is 0.9, right? So can you see, initially when you set total flow equal 1, okay, so I get this maximum congestion, can you see, 0.2, 0.209, okay? This is the one that I put here, G0. Okay. From there, I can get the K1, kappa 1 here. So this is the one that I set. So if the total maximum congestion becomes 0.9, then kappa 1 is exactly this value. Okay. So based on this, now what we will do, you set the total flow in the network does not change. What does it mean? The total demand, okay, is freeze. Within 1 year, you need to operate this policy. Okay, then we can compute. So this is the policy that we need to do within the same year. So kappa 1 does not change, right? So this is the new policy set. From this policy alternative, CA, with this capacity matrix that you change, I compute the flow matrix, the new flow matrix. Okay? So this is the CA, I compute the new flow matrix. Okay? The target is still the same. Okay, so then I get the new congestion level, which is 0.8, and which is smaller than 0.9 that you initially set. So you get the idea or not? So yeah, from there you can also compute the others. Yeah, you can compute the FARP index and so on. So this is very nice. Okay, you don't even need data, isn't it? Huh? So all you need is actually from the policy and the initial capacity matrix. Okay, I can estimate the congestion level, okay, the alternative scenario, and I can compare whether this is actually better or not. Can you see that? Amazing, no? So it changed your mind. Yeah. Earlier, you always say, I don't have data. Then I cannot do it. Now I said, now you don't need data. All you need is the network data. You can always simulate based on network data only. Remember, the supply changes the demand. The supply change the behavior. That's exactly congestion redistribution is about. I understand it's a new concept, so probably a little bit difficult to grasp. Yeah. But over time, when you practice again and again, then you start to see the merit and the benefit of this new concept. Tell me what you got so that we can discuss more detail.
Can I try, sir?
Sure, of course. I will stop sharing and use share.
Uh, from the one on the module, I'm looking at the max congestion. It's 0.35, I think.
Mhm.
And what I got is, wait, it's 8.835, but I got 0.8334.
Hmm? So you want to reduce this
DE.
one? DE, okay. This is exactly the value that we have. Do we get exact the same as in the slide? 0.835, is that? No?
I got
Yeah, almost now.
it's almost.
Yeah,
Uh,
83, 83%, right?
yes, sir.
just round off error.
No changes below here, sir. Or I mean, no other.
You can go down and see all the matrices down there. There, all the matrices. Okay.
Wait.
So you can check the matrices if you want to see the detail.
Okay, sir.
Okay. So if you see those matrices and check the detail, then you will start to see, for example, comparing the congestion matrix before and after, you will see that the congestion is shifted, from one link to another. Okay, this is the induced traffic actually. Okay, so this is the congestion-based scenario, right? And then compare this with the alternative. See, initially 0.20% here, now become 19%. This one 90% AB, now become 83. So that's mean 83%. This one is very light earlier, right? 0.05, that's only 5%. Suddenly now become, or increase, yeah? Increase the congestion, become 0.80. So that's 8%, right? From 5% become 8%. So the congestion is redistributed to other place. Can you see that?
That 0.05, I mean that
Yeah, earlier 0.0593, right? This value now become this one. Correct?
okay, sir.
Yeah. Similarly, this one is 44%, now become 41. This is not congested at all, 14%, now becomes slightly congested. You can start to see the redistributed. Okay, so this one earlier is 20%, now actually reduced. This is earlier 6%, now become 8%. This is 14%, now increase, become 19%. Well, still lower than 0.5, that's fine, right? But this is the concept of redistribution congestion. Can you see that? Okay, we let other links enjoy other congestion, increase of the congestion. Okay, by reducing the most congested area. So in the real network, this is actually becoming better. Okay, that also means what? You need to open the gate of the closed residential areas. Right. If this is public road, then it is public road. They are not supposed to become private road. And if you start to see the whole systems, okay, public road supposed to be government who maintain the road, correct? Okay, then if the government maintain the road, okay, when say certain development want to propose certain development, okay, initially the developer is the one who create the road there. Okay, that also means at certain point, okay, that road in that development will be turned over to the government, correct? Okay, so in that case, the government will start to maintain. So if you can start to see the whole picture, okay, the government will not allow to create a new subdivision unless the government have capability to maintain in the future. Can you see the feedback loop here? Okay, without that, they will just agree and agree without thinking of the future of the whole system. Okay, when you agree of something, there is a responsibility that you need to maintain later on. Okay, the purpose of government is not just to tax you. but to govern. Right? So, any question, any comment? Can you start to see how the congestion move to other place? Yeah.
Yes, Prof. It's much clearer now that you showed the redistribution of the congestion. It's
Yes.
much
So
clearer.
later, yeah, in your group projects, yeah, maybe next week when you report it, tell, yeah, yeah. Today is just key finding, but during in your paper, you tell, yeah, how it moved actually. Yeah, the congestion moved from this place to another. Can you? Okay. So with that, you start to understand the key concept. Yeah. How about others? Any other comment? What did you learn? So I want to know some. Several interesting policy analysis. Yeah, you go to the policy analysis slide. Okay. So yeah, so in this lesson, I want to discuss several applications of IFN for transportation engineering and planning. Okay. So first thing first, yeah. The network is now dynamic, yeah. So meaning that dynamic network means you can add, you can remove the links, yeah, you can change the weight of the links and so on. Okay. So you assume all in this scenario, yeah, you assume all the links have equal capacity. Let's make it like that. Yeah? So then, of course, the flow supposed to be identical to congestion. Yeah. So now we do what is called what if analysis. Okay. What will happen if you add a link to congestion in the network? Yeah. What adding link reduce or actually increase that congestion? Okay. Now the interesting part is not just one time, okay, but you want to find the optimum. Okay, this is an example of optimization. Okay, which link you should add in the network to minimally reduce the maximum congestion. Okay, do you get the idea? Say I have this dynamic network. Yeah, so initially I have this network, and say I add new link from 2 to 5 here. Okay, so let's say this is all the same capacity so that I can compute easily. Okay. So if you add a new link to 5 here, what is the IFN? Of course, IFN means strongly connected network and the flow is balanced, right? So initially all 111, it's a scale. Okay? When you add this, okay, then this will become 1, and 1 plus 1 become 2, correct? Okay, and then this one is continuous, so become 2 again, and then redistributed, okay, become 2, 1 and 1. Okay, the rest is the same, correct? Eh? So this is IFN. Okay, so you will see I add one link, the capacity is still the same, okay, but because I add one link, the flow here will increase over time. Okay, this is more congested than ever. So adding link can actually increase congestion level in the long term. Okay. Oh, now from this network, what will happen? I add another link here. Okay, randomly I add another link here. What will happen? Compute again the FN. Okay, and you see now this is the most congested. Remember, we keep the capacity still the same. Yeah. So this is now become 4 times than earlier. So you keep adding link. Apparently, you keep adding congestion. Is it true that adding link is actually uh, make condition worse? Okay. So again, I add another link here. Yeah, from C to D. Okay, and it become really worse. Now become 6 times. Is it true? Oh, not always true. Yeah. From here, what will happen? From D, I make 2 possible alternative. Yeah. Go to E or go to F. Okay. From D, I can go to E or go to F. Yeah. So if I go to E, that means I add this link. From 6, now reduced to 3.5 maximum congestion. Right? But if I go from D to F, okay, from 6 will become 4. Can you see that? Why the flow represent maximum congestion? Why the flow represent the congestion? Because the capacity is still the same, right? That because flow divided by capacity represent congestion. So this is represent congestion, correct? Congestion is just VC ratio. So flow divided by capacity. So capacity is still the same. So in this case, the same. So we can see, okay, not always adding link actually increase congestion, can be reduce congestion depending on where you add the link. So that's why you need to simulate first, okay, to get the optimum result. Do you get the idea or not? And any comment about this? Yeah. So in that previous dynamic network, yeah, we use minimum flow 1, yeah, for our network. Yeah. Yeah. So another example, this is probably you need to find. Okay, practice. Can you practice this? So this is the base scenario. I have 6 nodes. Yeah. Okay. And I declare the kappa, the total flow in the network is 27. Okay. So if you look at this, the maximum flow is 6 here. Yeah, it is link PA. So this is wrong, not AP, PA. So now can you add one link, yeah, from which node to which node, okay, that will have the greatest reduction of the maximum flow. But keeping the total flow kappa 27 constant, meaning total demand constant mean within the same year. I want to implement this new road. I don't know which road you need to find out. In order to make the reduction of the maximum flow is the greatest. So you can try one by one. And then, you have the tool, so I give you a few minutes to try. Can you? And once you finish, you show. You share your screen. Is that okay? It done. This is only a small network, so you can actually do iteration manually, right? But in the real network, you need to do some kind of small programming, yeah? Okay. That's why I open the source, yeah, in Python there in GitHub, okay, so that you can also, if you want, so you can do optimization on it, because to optimize the whole network, you need to go. So the technique is simple. So you try, okay, search. This is the base scenario that you have, right? So you search, okay, every two nodes that you have, okay, will be connected. So, for example, here you have a BA, then what will happen if I add AB? Okay, what will happen if I add here DA and so on? So the one that you did not have yet, so you try one by one. Okay, so then you will have, yeah, this is based on my search, so not necessarily correct, so you need to check that. Okay, so the best link that I add CA here, yeah, it will improve the congestion, yeah, from say 22% here become only 16%. At least you try this so that you will get exactly the same number. Reality, you need to check one by one. The value is simple, yeah. The kappa is given, so 27, right? 27 is total flow. The initial maximum flow here, links 6, right? Then I got this value then you compute the maximum congestion of this. And you need to enter this network into the matrix. That's the key.
Sir, I
Yes,
have a
yes.
question.
Sure.
For that problem, we can use the lab, right? The add
Yes,
link. We just
yes,
have to enter the base matrix, then
yes.
add CA as a link.
Yes, CA as a link.
Can I share my screen, sir, and ask?
Sure. Let's share your screen.
Let me know if you see it, sir.
Yes.
Did I use the correct lab add link?
Let's check. So you have, let's see, from A you go to D and E, right? 3 and 3. And then from B you go to A. And then from C you go to E. From D you go to E. 3, correct? Yeah? And then from E you go to B, C, and F, correct? And then from this one you go to only E. Okay, so you can also check the operator here if it's already ideal flow. So you check it.
Here.
Yes, is it ideal flow?
Yeah.
Yes, it is, right?
Yep. Yes.
So
Then I have.
then
We will add the CA plus 1.
CA, yes.
Then, um, it says here that the alternative scenario is worse than the base scenario.
CA. The alternative scenario is worse. Oh, two lane, at 2 lane.
Okay. Okay.
Yeah, it's still worse.
Sorry.
Oh, no. The base scenario is 0.8. The alternative scenario is 0.7. So it's improved. Oh, in terms of average congestion, but in terms of maximum congestion, it's
Okay. Okay.
it gets worse. Okay.
Okay. So we can either compare it like to the either in the
Yeah,
average
actually, this is worse in terms of
maximum.
maximum congestion.
Okay. Okay.
Okay, thank you.
Thank you. I just wanted to confirm, sir. Thank
So
you.
can you check the operation on the right side? Is it also actually
CA. Yes, sir. It added 2 lanes in the CA.
Yes. Is it ideal flow?
It's not ideal flow.
That's the problem. So uh, if you add that, so you need to make it ideal flow because you are computing based on congestion. So if it is become an ideal flow, it will become like this value in the slide. Can you see? PA become 4 lane, and then C
Mm.
become 2 lanes
I,
to make it improve. The problem is you are putting in the capacity matrix, okay? But when you compare, it's actually we need to compare the flow rather than the capacity matrix. So in that case, probably you have used the different tools. Can you go to, because you want to get the so here, capacity congestion. Yeah. Can you go to this tool? I will send you in the chat. So copy the one that, so open in the new tab. Okay. So open the new tab. Okay. And the matrix that you initially set, you can put it here. And the total flow, you need to set it 27, right? So you can put it in PCU per hour. Can you try? So the lab tool that you used a while ago is totally different purpose. No? You want to share your screen again so that we can.
here, sir.
Yeah. So okay, initially you already did this. So capacity it is already. So can you see if the capacity matrix that you have here is the same as your ideal flow?
Here, yeah.
No, no, no. In that capacity to congestion. Yes. So this capacity matrix, because you are using capacity matrix. So this one you have because you are setting this because you don't know the capacity matrix, right? So you are assuming this is the congestion, the flow. Then you go down and check. There. Is it the same as this one?
3, 4, 2. Yes, sir. It is the same.
Yes, exactly the same. Okay, good. So this is now you screenshot this. Okay, as your first case scenario, right? Okay. Okay. Including the congestion matrix. So you can put the congestion there. So you see if this is interesting. If your capacity matrix is exactly the same as your ideal flow, the congestion matrix is exactly 1, 1, 1, 1. Can you see that?
Yes,
Yeah,
sir.
of course, right? Because congestion is basically flow divided by capacity. Congestion matrix will be uniform. That's the idea. This is called free matrix equilibrium. Okay, now you can add, what is that, CA?
CA.
And then now you calculate again. So your capacity changed, okay, but your ideal flow will change now. It's not the same. So now you can check your maximum congestion down. Is it worse than compared to before? Oh yeah, it's worse.
Yes.
Okay, the slide is wrong. Yeah. So it's not improving, you know? Actually make it worse. Yeah. So my slide was wrong in that case. Thank you. I will correct it.
Thank you, sir, for confirming.
Yeah. Yeah. So
I was a bit confused a while ago.
no. So in that case, my slide is wrong. Yeah. So the calculator is the one that correct. Okay. So another idea. Okay, in the slide, can you check? Is the long-term prediction. Okay, this is another idea. So how are we going to use? Okay, we combine actually the traditional four-step models, trip gen and so on, with IFF. Okay, you remember you learned about regression last time, right? Okay, so how are we going to use that? Now we want to integrate all, okay, that we learn in one semester, okay, into this example of policy analysis. Okay, so it's my sharing. Okay, share to the slide. Yeah, yeah. This answer is wrong. I will. So here, so you can practice this. Okay, this is an example of the result of regression. Okay, so this is called econometric model. Okay. So this is amazing. You know why? Because you will implement the same rule, yeah, the same policy, okay, whatever policy it is. So in here, the example of policy is at one lane on the most congested link, yeah, when the maximum congestion reaches 0.9. Okay, so we will not change the network structure. No add link, yeah, no remove link. Okay, only adding lane. Okay, this is an example. So no change in the network, and you use that calculator that you have. Okay, so we set the capacity per lane 1,500. Okay, let's assume this is the one that you get from your statistic office. Okay, so this is a small network. Okay, so this is the network that we have. Wait, I will clear the drawing. Okay, this is the network that we have. Okay, only 5 nodes, and this represents the number of lanes. Okay, so you need to change this into matrix. Okay, and because one lane represents 1,500 vehicle per hour, so you have one lane, then become 1,500. You have 2 lanes, of course, you multiply by 2, so become 3,000, and so on. Okay, so let's start the base scenario in the year 2000. Okay, and you have this model, and this one. This is trip gen, yeah. So you have the model of total demand in the network at time t. And so kappa t, that means total demand in the network at time t, equal to regression model. So because this is very small anyways, I just make it up. Okay. So it depends on the population of human and the population of car. Is that okay? So the population of human, okay, initially, and this is a small town, so 1,200 person. And initially, the population of car is 550, right? And then the population of human assumed to grow 5% per year, but the population of car 7% a year. Okay, so what you will do with this? So what you will do with this is you create a table, okay? So you create a table in Excel. Can you? So the table in Excel will look like this. This one. Can you make a table like this in Excel? Based on this model. Okay. So initially you just put the year 2000, and this is the initial value that you have, right? And then you input the value, say 1,200 here. The car is 550. Okay. You will get kappa T, total flow in the network, 10,000 something. Okay. And then you just increase, okay, this one, yeah, up to 2030 or 2050. You make, and then this one increase 5%, right? And this one increase 7%. And then you can compute the total flow for each year. Do that first, can you? So let's do the econometric model first. I want you to do it step by step. Yeah. Can you make it? Then like this. Can you see my Excel? No, I haven't shared. Yeah. We create this. This is just +1, right? Here you just regress using the growth factor that earlier plus population plus the growth, right? So the growth is the earlier population. And this one must be with $string because not change this number. Okay. Same thing with the start population. Okay. And then this one depends on our model. It depends on the row, columns. Same thing here. Depends on the possible. Make this first. Anyone want to share screen?
Sorry, sir. Can I
Yeah.
ask what's the third column again? Was it flow?
So, wait, check. Excel. Yeah. This one, the total flow.
Yes, sir. What's total?
Total flow is based on the model.
Okay.
Kappa, yeah. Kappa is depends on the population, and then depends on the car, and then plus the intercept, right? So 3,500.
Okay.
Yeah. 3 and 7 represent the gradient. The slope, yeah, of population and the slope of in regression model. Yeah. So can you create this table?
Can I have mine checked,
Sure,
please?
sure.
For a while. I'll zoom in.
Okay, good. So you make it, right?
Yeah, with formula.
Yes. Okay, so now you get the prediction of the flow for every year. Okay, the question is how are you going to use that, right? To predict. So remember this. This is interesting because now you can predict two things. No? First, if you will predict the location. Second, you will predict the time. So you will predict when and where. So interesting. Yeah, space and time. This is never done before. Okay. So now you get the matrix of that network. Okay. So the network, can you make the matrix? The network. So can you create a new seed probably? Okay. So what I'm doing, I'll share it. What I'm doing is I input the network here into capacity matrix, right? Okay. So that so yeah, A to B is one lane, yeah. That, okay. So okay. And from here, from the capacity matrix, I can compute the flow matrix and I can compute the congestion. This is already different year. So initially you have B, C. C is only 2. Yeah. And then B to E. E also 1. So this is after so many years it changed. Because our policy is to put if the congestion level reach certain number, say 0.9, then on that link, we will increase one lane. And that's the policy rule, right? So we will simulate the policy rule. So can you make this network into the capacity matrix? And then you can compute the flow and flow capacity. Yeah. Or you can put it in the calculator there. Okay. So what happened is once you have this capacity matrix, and initially this is what I'm doing. Okay. In the year 2000, okay, based on this capacity matrix, and you get the K0 is 10,000 and 50 while ago, right? In the table. Okay. at that time, okay, so if you compute the matrix, you will get this value. So maximum congestion is 0.61, which is in link DC. And you see in the link DC, in the initial year, which is year 2000, you get the maximum congestion 0.61. So then you want to ask, okay, when this 0.61 will become 0.9. Okay, using IFN, this is very easy. Okay, so if you compute the maximum congestion 0.61 in link DC, okay, when it will become 0.9, okay, it will become 0.9, okay, so you calculate the scaling, 0.9, the one that you want, divided by 0.61, the one that you get, okay, that is 1.29 over 61, okay, this is, so you get the scaling, okay, once you get the scaling, okay, you multiply this scaling with the initial total flow, yeah, so you will get 16,200, okay, so this 16,200, then you go to your table there, okay, in 2009, so if this is the beginning of the year, 2009, it will become 16,162, but this is already 16,200. That means probably what year, what month is that, or what date will reach this value? It will happen in 2009. Can you see that or not? Okay. So once you get this value, 16,200, now you put this as an input. So when you put that as an input, you will get exact. G equals 0.9. Okay. Now, based on the policy scenario, whenever G, the congestion level reach 0.9, then in that link, we need to add lane, isn't it? Right? So what is the link that we need to add lane? DC. There. So then we add one lane in link DC. Yeah. So once you add from 2 lane become 3 lane, okay, then everything changes, isn't it? So then the stochastic matrix change, the flow change, and then the congestion level change. So in link DC, okay, earlier before you add congestion, you add lane, it was 0.9. Now becomes 0.6. Oh, okay. If you add in the most congested link, yes, that links improve. But actually, the one that you did not see most of the time is the congestion shift somewhere else. Now become B, C, and BE. Now become 0.82. Earlier was 0.55. Okay. Now it increased, becomes 0.82. Okay. So that's okay. 0.82 is not 0.9 yet, isn't it? So then again, you will ask when it will become 0.9. Okay. Then you divide, to get the scaling the same technique, yeah. So when the 0.82 will become 0.9, you get the scaling. I repeat the same thing, often different number. So 0.9 divided by 0.82, this is the scaling. You multiply, yeah, by that 16,200, yeah, this is in 2009, right? So now become new kappa, which is 17,780. Then you go to the table a while ago. When it will happen? Okay. Can you do that? Is it clear or not? So 17, how much? Oh, 17 something. So that will happen in 2011, isn't it? Yeah. So you see, you can predict time. Yeah, this other time, right? Yeah, 2011, and the space. Yeah, which one is the one that actually? Yeah, this is the result. I summarize this. So when it will become congested? Oh, it will become congestion. This one, and then you reduce it. Then the congestion shifted somewhere else, and so on. I can predict the time and the space. Which link? Amazing or not? Huh? Okay, try so that you, at least 1 or 2 years, you can try so that you can understand. You get the idea first. This is the real urban planning, yeah, of transport planning, isn't it? Because you can predict, okay? And if your prediction wrong, then probably your model is wrong. It's okay, you revise, no problem. No? You're not always right, but at least this is science, so we know how to improve. Okay? But if you talk about average congestion, how can you know the average congestion? There is no way to get the average congestion over the entire network. Okay, but if you get or average travel time, average speed, you cannot get. But if you get maximum congestion, and then you know the one link only, right, or two links only, then you can go there and check in that year, okay, your prediction is correct or not. In fact, you can actually check the time view. Okay, so say 17, yeah, initial year, yeah. So your value is how much a while ago? Say 17,750. This one, 17,750. So yeah, this is 2011, right? So if you minus this value, okay. So this is probably January, isn't it? Where this? Okay. Oh no, you see the difference between this minus that. So in 1 year, supposed to grow about this value, but your prediction said only 19 out of this value. So I will just get the value. By this one, so this one I multiply by 12. This is only, so if you assume equal per month, okay, if you assume equal per month, so I will divide this one by 12. So 1 month is about 72. Yeah. So you are only, I think, 19 out of this value. That means you are in January. So January 2011, you can check in the field, okay, whether you can get this value or not, yeah, or the maximum congestion. So in this link, okay, did you get this value or not? So or you can monitor in certain place. So it's not so expensive to monitor just one or two places. But if you want to monitor the entire net, that's so expensive. I hope you get the idea. Tell me what do you get and give me feedback.
For me, sir, what enlightened me was just by adding the lane, the congestion was redistributed somewhere else.
Yes.
Although the max congestion is reduced from 90 to 82, uh, there's a congestion redistribution. So that's
Yeah, that's called induced traffic,
reduced
because
traffic.
yes, even if you improve certain links by adding that lane, induced traffic, that means certain other links in the network actually suffer. That most of the transport planners did not think that way. That's the problem. You are only solving one place, but you did not think that other place suffer because of your input. We are not in one link case by case. We need to think over the entire network. That's the mindset that we need to start to think in terms of system, not project. Okay, say your project is successful, but the entire system suffer, then you cannot say that your project is successful. Correct?
I have a question, sir, because in congestion redistribution,
Mhm.
we're reducing maximum congestion, but the average congestion is increasing.
Not necessarily. Can be increased, can be reduced. Might increase.
Might increase.
So my argument is, if you start to use, this is what traditional way to do, yeah, average congestion, average speed, average network speed, average travel time. Right? But when we said average, okay, you need to check the entire network. This is the one that is difficult to monitor. Okay. Well, you said maximum, then you only point to one or two places, right? Then easy to monitor. This is the argument. Darling.
One comment, sir,
Uh,
because I'm thinking about EDSA
hmm.
and
You keep adding widening or improving EXA, right? So, but you did not think the entire Metro Manila. That's why I told last time, you forget about EXA, improve the other place. and then ETSA will improve by itself. Think in terms of network, not just one or two links. It is mathematics. I did not. Okay, you can see the mathematics tell that. Okay, so then you can see we can prove it. But okay, think this way. Everyone have their own opinion in terms of transportation and congestion, correct? Even jeepney drivers suffer a lot, so they know, okay, their own opinion. What make you different from a jeepney driver as an engineer, as planner? Is one thing. You can compute based on science, they cannot, correct? Okay, their opinion is personal opinion. Your opinion is based on science, which is objective, based on data, okay, repeatable. Their opinion may not be repeatable. Maybe their opinion is correct, but we don't know. Okay? Based on science, you can communicate to others. That's why you are in university. That's your advantage, correct? Otherwise, everyone will have their own opinion about traffic, correct? Because everyone suffers, so everyone knows. But knowledge about traffic doesn't mean that you can solve, unless you can justify and prove what you are doing or your opinion is. Correct. Without proper tool, without proper mathematics, how can you prove that? It's just an opinion. Everyone can say anything. But with this mathematics, so you can check, you can prove, you can simulate, you can optimize. That's your advantage. It's not just opinion. Otherwise, you have no different with other people. I mean, in terms of competitive advantage. Yeah. I'm not telling that they are lower than you, no. But at the same time, okay, why you go to school, isn't it? So that's the competitive advantage that you need to preserve. Okay, can they predict where and when? No, you probably can predict maybe just if 1 or 2 years, so there is an error in your prediction. That's fine. Okay, we are not saying we are perfect. Okay, but the ability to predict is not just an opinion that they can state whatever they want because you can prove that. That's is the essence of transportation modeling, isn't it? We, we have a half hour, so your time uh, to do this and to present your project. And this is our last class. So go ahead, who will present first?
Hi, sir. Maybe we can go first.
Go. Do you need permission to share?
No, sir, I'm just converting it to a PDF so I can
Okay,
use it.
okay. Hmm, Okay. Go ahead.
All right. Thank you. Maybe we can flash this in full screen. Is that possible? Or
I think this is the
yan na yan. Okay.
um,
Sige. Yeah. Sige, sure. That's okay. Yeah. Hi everyone. This is Kenneth Mangalino. My group mates are Justin Hasigawa and Blaze Morales. This is our final progress report for our study. We actually revised the title for study. So it's now Peak Our Passenger Flows in Cubao, Understanding Capacity Limitations and Policy Pathways. Next slide, please. Just a brief recap. So our objective is still the same, which is to recommend policy to improve the network flow and reduce congestion during the evening peak in Cubao. The special scope is the Cubao Modal Hub in Quezon City. Next slide. So in terms of observations, we focus our study on four different modes of transport, which are rather the buses, the jeeps, the UVs slash vans, and trains. So for buses, vehicles per hour, and the estimated passengers per corridor were checked. So some key findings, we found out that
Hmm,
Montalban and Rodriguez corridors show high estimated passengers with 200 to 400 pax per hour. And then bus capacity is fixed 23 seats per plus some passengers are standing, creating possible bottlenecks. For Jeep passengers per hour is 682 total, then 490 for UVs and vans. For trains, there's a high estimated passenger system-wide, but Cubao is not congested in the evening, based on our field observation.
This is
Because many
this is flow. This is the flow or fare. Only 600 passenger per hour or less than 500 passenger per hour. Very small.
That this was 5:30 to 6:30 observation time last Tuesday. Yeah,
Morning or evening?
evening, sir.
Oh, okay.
In the morning, it's more. We didn't observe the morning, but they say that it's more congested.
Yeah, okay. Pretty small. Okay, go continue.
Yeah. As I was saying, for trains, the table is not shown here, but consistent with what Blaze was talking about, there's minimal evening train congestion. All waiting passengers were able to board due to high capacity of the trains. So for trains, we have two lines that are crossing Cubao. We have MRT and the LRT2 line 2. So it's observed that many passengers alight in Cubao, and trains don't cause upstream congestion for this time window.
This is 1 hour, not 15 minutes or 10 minutes, no?
It's 1 hour, sir.
Um,
Please confirm na lang, please.
sorry for the MRT. This was only observed for around 2 trains. So that's around MRT is around 30 trains per hour. So that's around two. How many minutes is that? Around 10 minutes, I think.
Okay.
Yeah. So 5 minutes per train. And the LRT was not observed, but all of the people waiting in the MRT were able to load
Hmm.
onto the train. So there's nobody waiting afterwards, except for
Okay.
the people who are rushing and trying to catch the train.
Maybe during your time of observation, it's not congested. Yeah. Yeah, so minimal trade. Okay. Thank you.
Can proceed with the next slide.
Yes.
For some other findings, so it was observed that traffic within the Cubao network flowed smoothly. Vehicles were generally able to clear intersections within a single green phase. There are also signalized intersections operated on a four-phase cycle, and we observed that congestion was most severe along EDSA compared to internal network roads in Cubao. So the passenger mix is a bit skewed because there was an event. It was a basketball game happening in Araneta Coliseum in Cubao. So we noticed that there are a lot of students boarding the um, vehicles. So again, no queues were observed from 4 to 5 p.m. Queues began forming after 5 p.m., particularly on routes with slow dispatch, for example, Luzon to Cubao line. Next slide. Oh, sorry. We forgot to skip this. We already showed the tables. So full disclosure, sir, we're still in the process of polishing our models, but based on our observations, these are our hypotheses. So first hypothesis is sorry. Hello.
Hmm.
Hello, can you hear me? Sorry, I
Yes, yes.
got disconnected. Okay, great. So the first hypothesis is that the bus system is simply undersupplied during the peak hour. When we look at the observed passenger volumes per corridor, we're seeing several hundred passengers trying to board within a single hour, with the number of buses available, and the seats per bus don't grow proportionally. We believe that this mismatch suggests that the queues and the delays are likely caused not by traffic flow itself, but by insufficient vehicle supply at the terminals. So our second hypothesis is that fare adjustments alone will not meaningfully change passenger behavior, in that this will have limited impact on congestion if capacity remains unchanged. During peak hours, most passengers are price inelastic, so they need to get home, and they don't really have flexible options, especially in this area. So even if fares go up or down, the behavior we're likely to see is the same. Passengers will still line up, and the bottleneck remains on the supply side. This means that fare policies should be evaluated together with capacity interventions, not in isolation. And our last hypothesis um, is that even without fare changes or adding new infrastructure, improvements in terminal operations, like, for example, dispatching, queue management, and maybe better allocation of spaces, could lead to noticeable reductions in waiting time. If loading times per bus decrease, we believe that the entire system becomes more efficient even at the same capacity. So before our next steps, we'll continue building the model. Go- for the purposes of this discussion, we'd like to ask your feedback, sir, on our
This is
approach so far
this is
and
supposed
our latest.
to have say multinomial logic model or something for the fare, right? So this is mode choice model, right? Did you make it?
That's correct, sir. We're still polishing that model, sir. Sorry, we're unable to present now. But yes, that's included in our approach.
Do you think you can finish it in 1 week?
Yes, sir. Yeah, we can finish it
Yeah, okay.
in time for
So
our submission.
okay, so I want to ask you something. Uh, in one train, how many cars? How
MRT
many?
is 4 cars.
4 cars
LRT,
only?
4 cars for MRT.
MRT.
LRT, that's MRT, 4 cars. But
Okay.
LRT is not sure.
Okay, say assume 4 cars. Per car, how many passengers capacity? Standing and sitting. Do you have?
Uh, I don't know per car, but it's around 1,600 according to online sources.
1,600?
Wait, let me check again. Sorry.
Maybe I can chime in.
Yeah, okay. Because your number doesn't match up.
Yeah. Actually, per car, it's 74
Okay.
seating capacity, and standing is around 300 to 350.
Okay,
That's
so
according to MRT's website.
in that case, let's say assume 350 times 4, right? That means 1,400. Is that correct? In one movement, and you said a while ago, like 8 every 10 minutes, right? That means, say you have 5 or 6 trains, yeah, each with 4 cars. So that means you will have 1,400 capacity, multiplied by, say, 5, right? That's around how much? 7,000 plus, right? But your number of passengers was only 1,600. That is very small. Correct or not? Comparing the demand compared to the capacity, the supply. So your number does not match. And then uh, you have this hypothesis, which does not match with that number. But anyway, this is just practice, so try to create a model, okay, and then try to do this hypothesis changing and so on. And I want to see if you really understand the lesson in this semester. Yeah. even if it doesn't really much, that's okay. I don't really mind with that. Yeah. But if it is real project, so I just want to tell your number does not much.
Copy,
That's
sir.
thank
We'll double check.
Yeah.
Sorry, Blaze. What were you saying?
yeah, noted, sir. We'll we'll double check.
Am I wrong or right in terms of computation? I mean general only. So
For
three,
the MRT and LRT, sir, I think we really need to revisit that because uh, I, I think we're still trying to, well, for that one, we weren't able to count really the number of people. So
right.
yeah, yeah,
Maybe I'm wrong in the communication. So when you said 1,600 plus, that is only incoming and going, or including the one that inside the train. That's different.
it's yeah, I think it's really supposed to be much higher.
Hmm.
Yeah.
So probably uh, what you said is only OD, or going in and going out. Is that correct?
I think I'm not so sure. Because there's also the east. There's two directions for the train, so we just have to, I think, revisit that number.
Okay.
So there's
So
the eastbound and the westbound and the north and south. So it's actually doubled if we think about it.
okay. So please recheck.
Yes, sir. Thank you.
Yeah. And what else? Okay, so no conclusion yet, no analysis yet.
Yes, sir. That's actually it. We'll probably reach out within the week.
Okay,
Might have some questions to
sure.
final
So
answers.
you can contact me anytime. So
Okay, sir. Thank
yeah.
you.
Okay. So for the next group, thank you for this group. So how about other group? Yeah.
Hi, sir. Sorry, I don't think we will be able to present today. It's only the two of us right now here, and the one who was tasked to present and run the alternative scenarios isn't very responsive. We were trying to
Oh,
contact
okay.
him all day today, but he isn't responding. So I think we will
Oh,
just
okay.
schedule a meeting
Okay.
before
So
Friday.
let's schedule a meeting next week.
Yes.
Yeah.
Sorry, sir. Thank you.
Okay then. So okay. So for the final exam, okay, let's just go. So for the final exam, so the coverage is all from beginning until today. Okay, there are 25 or 30 questions, multiple choice. You can take it from morning until evening, but within the same day. Don't ask me for leniency. I already gave you very lenient compared to other professor, isn't it? Okay, so you can have two attempts. So first attempt, but you can only get the grade maybe one day after. Okay. So and uh, within the same week, so you need to submit all the assignments, all the projects. Okay, and the around Christmas, I will send you the computation of the grade in Moodle, in Excel file, so you can see the computation. And there is something wrong, can you tell me? Okay, and once I upload to the UPCLS system, please don't ask me to change anymore. Okay, I give you a chance. Okay, but if you did not submit, so you will see 0 in grade. Okay, so and if you are late in submission, of course, as we mentioned in the beginning, so one day is minus 1%, right? So, okay. So thank you for the semester, guys, and I hope you enjoy the lesson in this course. Yeah, time. So maybe if you want to join the next course, 5/8, that is about decision making, game theory, little bit finance. So, on Thursday, next semester, we start January. Okay. Yeah, still online. Okay, so is there any feedback from you about the entire semester? Is there anything I need to improve? So you tell so that I can have. Yes, please.
I wanna thank you, sir, for sharing your knowledge. I really learned a lot, uh, especially in the traffic theory. The it's a lot of math, so uh,
Sorry for
very
that.
very challenging course. I don't think I've taken so much math in and
Uh,
yeah. So yeah, I just want to thank you for the
thank you.
exercises and what I learned also is the practice of the first the capacity, and then it's only later on that I really understood, and the green shields was cemented in in my
No problem.
thinking. So it took like maybe the whole semester for me to understand green shields really. So
Okay.
uh, but it's the practice that the continual repeating and then practice and of course the making mistakes and then your feedback also.
Right.
So I really learned a lot.
Thank you. Appreciate that. So I probably need to put more practice in that case. Is the lab helpful?
Yes, sir, it's helpful. I think for me, I'm kind of also I'm afraid to make mistakes as well. So I'm just sometimes I'm a little bit conscious. So yeah.
So it took me a lot of times to create the lab.
Sir, by the
Yes.
way, can you still access the lab after this semester?
Oh, the lab is public,
Okay.
not just for you.
Oh.
Right. But even if public does not mean that they can understand the lecture. Anyway, the lecture is also public in YouTube, so but not so many people subscribe anyway. Probably because 3 hours is boring.
The live sessions are much more engaging than the videos on YouTube. So for me, I really get more engaged when there's the live session compared to just
Oh
watching YouTube.
yes, of course. So that's why you need to attend the class, even if it is online and even if it is also in the YouTube. Okay, the live session with the practice. I hope that's help. Okay, so if you have a evaluation, so you can do so, photo. Okay, and anytime if you want to ask, so you can ask. You know my personal number, so there's no problem with it. Okay, so thank you for the semester and please do well in the final exam. It's not easy exam, even if multiple choice. Okay, so okay, that's all for today and for the semester. Thank you very much.
Thank you, sir.
Bye.
Thank you, bro.